Hello, and thank you for joining me virtually today. I'm Azalea Raad, and I will be talking to you about our joint work with Lahav and Viktor Vafeiadis on persistent Owicki-Gries reasoning. Let's start with a quick introduction to what persistency is. Traditionally, computer storage is divided into two categories. On the one hand, we have the RAM, which is faster access to read and write, but it is volatile in a sense that it loses its contents after a power failure or a crash. On the other hand, we have hard disk drives, which are slow to access, but they're persistent and preserve the contents across power failures and crashes. Non-volatile memory, or NVM for short, is a hybrid of these two worlds, bringing you the best of both. They are fast like RAM, but they're persistent like hard disk drives. In fact, NVM, or persistent memory, has become so prevalent that recently mainstream architectures such as Intel and ARM have extended their models with persistency features. In our recent work in POPL 2020, we formalized the persistency guarantees of the Intel x86 architecture and developed a model called PX86 for persistent x86. And the way we did this was by extending the original x86 TSO model with persistency features. It is important for this talk for us to have an intuitive understanding of what PX86 is, which itself requires an understanding of the original x86 model. As some of you would know, we can think of the x86 architecture diagrammatically as shown on this slide. On the top, we have multiple threads of computation or multiple cores, and at the bottom, we have the memory, which is shared amongst all threads. Now, each thread additionally has a local buffer known as a store buffer that is only accessible to the thread. So every time a thread issues a write, it will be added to its own local buffer, and it's not immediately propagated to memory. Now, the writes in the local buffer are only visible to the thread, and at some future point, they will be non-deterministically propagated to memory in FIFO order, by which point they become visible to other threads. As a result, every time a thread issues a read, it will first check its own local buffer to see if there is an entry there, otherwise it will go and fetch it from memory. And of course, since the local buffers and the memory are volatile, if there is a crash, then the contents of memory and buffers will be lost. You can think of the PX86 model as an extension of that x86 diagram with an additional layer known as the persistency buffer, or the P buffer. So as before, every time a thread issues a write, it will be added to its own local buffer. Now this time, the writes in the local buffer will be propagated, but instead of memory, they will be going to the P buffer in the FIFO order. The writes in the P buffer are now visible to all other threads, but they are still volatile. Now, the writes in the P buffer in turn will be propagated to the memory at non-deterministic points in time, by which point they remain visible to all other threads and they become persistent. Now, this propagation from P buffer to persistent memory is no longer necessarily in the original FIFO order. It is, in fact, in the FIFO per location order, meaning that the writes on each location are propagated in the same order that they entered the P buffer, but the writes on different locations may be propagated to memory in an arbitrary order. And similarly, every time a thread issues a read, it will traverse this hierarchy as before. First, it will check the local buffer to see if there's an entry there. If so, it will fetch it. Otherwise, it will go to the P buffer. If there's an entry there, it will return it. Otherwise, it will go all the way to memory. Once again, if there is a crash, since the buffer and the P buffer are volatile, they will be lost, but the contents of the memory is now persistent and they will remain visible after a crash. Now, of course, it was important to understand this and formalize the persistency semantics of Intel x86 as we did in our POPL 2020 work. But when it comes to reasoning about the properties of persistent programs written on top of PX86, this is far from ideal. Specifically, this model is very low level, and any reasoning at this level involves reasoning at the level of program executions or traces, which is not ideal and makes it difficult to verify high-level programming variance. So ideally, what we want is a high-level reasoning mechanism, such as program logics, that allows us to reason at the level of program syntax and not program traces, which will make it simpler to verify high-level invariance. So this is the gap that we were trying to fill at the beginning of this work. And when we turned to the state of the art, we realized that there is indeed no program logic for persistency in the literature. So we decided to develop and devise the first program logic for persistency. And for that, we had two possible avenues available. First, we could do a high-level extension. And by that, I mean that we could take an existing program logic that is sound for x86, and then extend that to support the persistency features of PX86. Alternatively, we could leave our program logic that is stands for x86 untouched and instead change the low-level semantics. And by that I mean we could encode px86 into x86 and use the same logic as before to reason about px86 programs. And it turns out that for us, the second approach was simpler, and this is what we did in this paper. More specifically, our contributions are as follows. First and foremost, we developed an instrumented x86 semantics, which reduces px86, encodes px86 to x86 by removing the p-buffer component. And then we provided the translation mechanism that takes a px86 program and gives us a program on top of ix86. And as I will discuss shortly, this involved several challenges. We then built our program logic, persistent Owicki-Gries reasoning, or POG for short, on top of ix86 and verified several representative examples in the paper. For the rest of this talk, I will focus on our instrumented x86 semantics, or ix86. As I said, this involved several challenges that I will show you through examples. So first, let's look at a simple program where I assign x of 1 to x and 1 to y, and then the program crashes. Now, if originally both x and y hold 0 in memory, the question is, what are the possible observable behaviors after the crash? In fact, it turns out that there are 4 possible behaviors, as shown here, in the sense that if both writes were propagated to memory before the crash, I will see 1 for both, or if neither did, then I will see 0 for both. Or if the first one propagated to memory and the second one didn't, I will see x is 1 and y is 0. But most surprisingly, it's possible for me to see the second write having propagated, but not the first one. In other words, I can see these persists out of order. And intuitively, the reason for that is because, as we said, the writes in the p-buffer on different locations can be propagated to memory in an arbitrary order. In particular, let's look at this execution. So here I have only one thread of execution, and I have grayed out the other threads. So the thread issues a write to x, which, like we said, will be added to its own buffer. And then it issues a write to y. Again, it will be added to its own buffer. And these writes are propagated to the p-buffer in the FIFO order, in the same order that they were in the local buffer. And now these writes to the p-buffer will start propagating to memory. But like we said, the writes on different locations don't necessarily have to reach memory in the same order. So here, it's possible for the write on y to be propagated to memory first. Now, if a crash occurs at this point, then the contents of the p-buffer will be lost. And when I restart the machine, I will see the contents of memory holding x is 0 and y is 1, as shown in this behavior. Now, remember that by encoding px86 into x86, we essentially want to remove this p-buffer. So the question is, how do we model this out-of-order propagation in the absence of a p-buffer? So the way we dealt with this was by introducing 2 versions per location x. Specifically for each location x, we record a volatile version xv and a persistent version xv. And our translation mechanism says that every time you write to x, write to xv instead, and every time you read from x, read from xv instead. And to model this propagation from p-buffer to memory, we can say at non-deterministic points in time, copy the contents of xv to xp. So if I go back to my example, on the left-hand side here, I have the original program, and on the right-hand side, I have its translation. So I start with a state where everything is 0, so both versions of both locations are initially 0. Then I assign 1 to xv, so now I have xv is 1. And I now also have to account for this unbuffering, for this propagation of the volatile versions being copied to persistent versions. So when it is possible for me to copy xv to xp, so I can have xv either 0 for the case that the propagation hasn't happened, or 1 for the case that the propagation has happened. Similarly, I now write 1 to yv, yv is 1, and once again I account for unbuffering, and yp now can be either 0 or 1. And taken together, these 2 will give me the 4 possible outcomes that I wanted to. But there is another challenge. In fact, in order to avoid such crazy out-of-order persists, Intel allows you to use something we call explicit persist instructions, known here written as flushx. So in this example, if I insert a flushopt between these two writes, this says that make sure all earlier writes in program order on X persist before all later writes. So here, this insertion of the flushopt makes sure the write on X persists before the write on Y, and as a result, I don't have this out of order persist behavior anymore. In other words, this flush X imposes additional ordering constraints in the P buffer. Now note that the flush X behaves asynchronously in a sense that when it's executed, it doesn't necessarily make sure that X is persisted. And as a result, it's still possible to see that X is 0. And so all flush X does is add in ordering constraints in the P buffer. And once again, since we want to remove the P buffer, the question is, how do we model this without the P buffer on top of x86? So as a naive attempt, we kept our mechanism and representation as before, and we said, okay, as a translation of flush X, every time you execute it, copy XV to XP. Now let's see what goes wrong here. So once again, I have my program on the left-hand side and its translation on the right-hand side. And I start by 0 for both versions of both locations. As before, I write 1 to XV and account for unbuffering. And now when I execute the flush, I will be assigning XV to XP, meaning that now XP will be 1. And once again, I assign 1 to YV and account for unbuffering, which means that YP could be either 0 or 1. Now, since XP is 1, taken together, this will tell me that give me 2 outcomes. Either they're both 1 or XP is 1 and YP is 0. In other words, we cannot model the behavior where XP is 0. And this is because this translation is modeling the behavior of flush instructions synchronously, which we know is incorrect. So we went back to the drawing board and instead extended our representation with an additional version for each location. So now we have 3 versions. With this new version, XS, the synchronous version, used purely for modeling flush instructions. Similarly, we adjusted our translations we kept the write and read translation as before. Now, every time we execute a flush, we copy XV into this intermediate new version XS. To model the unbuffering, remember we have 2 types of unbuffering. To model the unbuffering from buffer to persistent buffer, we copy XV to XS. And to model the unbuffering from P buffer to memory, we copy XS, the intermediate version, to XP. Now, for technical reason, this propagation, this unbuffering, has to be done for all locations at once, hence the overline notation. And intuitively, this is to make sure we capture all ordering constraints imposed by flush instructions. So going back to our example, now we have 3 versions. So let's assume that all 3 versions are set to 0 initially. I assign 1 to V and account for unbuffering. And this time the unbuffering involves from XV to XS and from XS to XP. So XS and XP could both be 0 and 1. Now next, when I execute the flush, I will be copying XV to XS, which means that now I have XS is 1, but XV is still 0 or 1. Next, I assign 1 to YV, which YV becomes 1. And now I'll have to account for unbuffering. So when I account for unbuffering, it means that I have to assume that YV can be copied to YS, which means that YS could be 0 or 1. But then I also have to account for the case where all S versions, XS and YS, are copied to their corresponding P versions. Now, since XS is 1, if this copying happens, then as a result, YP becomes 1, then XP will have to become 1 as well. So we get this invariant that says if YP is 1, i.e. YS being 1 has been propagated to YP, then XP must be 1, i.e. XS must have also been propagated to XP. Now with this invariant, now I have exactly the behaviors that I wanted from before the 3 cases as shown here. Finally, there is an additional challenge in that Intel gives us an additional explicit persisting instruction known as flush optimized. This is more or less, its behavior is more or less like flushes. It behaves asynchronously, but it has weaker ordering constraints in a sense that it itself can be reordered with respect to other instructions. So in this program, it was possible for me to order flush optimal after the write. And as a result, once again, it is possible to observe this weak behavior. Now, we could have gone back to the drawing board and once again extended our representation of these versions and our translation, but we found that that was rather difficult. So encoding flush optimal in this representation was hard. Instead, what we decided to do was rewrite programs so that instead of using flush optimal, they use flushes. And this rewriting will have to preserve the program behavior, i.e. we will have to rewrite it into an equivalent program. Specifically, when we inspected the code bases that use flush optimized, we realized that this is often done in a particular way, following a particular programming pattern known as epoch persistency. And in such cases, we realized that it is always possible to transform the program so that, and rewrite it so that instead of flush optimized, it uses flushes. And we developed this transformation mechanism and shown that it indeed preserves the meaning of the program, so that this transformation yields an equivalent program behavior when we replace flush optimize with flush. Now, this brings me to the end of my talk. I showed you a brief overview of our instrumented x86 semantics and how we reduce px86 to x86 by removing the p buffer. I very quickly told you about transformation mechanism for rewriting programs with flush optimized to ones using flush. What I didn't show you was our program logic, persistent Owicki-Gries reasoning POG, which is built on top of x86. So in a nutshell, here you can think of our pipeline as follows. Take a px86 program, which could potentially use flush optimized instructions, feed it to our transformation mechanism, and obtain another px86 program that doesn't have flush optimized instructions. Then run it through our translations to convert it to an ix86 program, and finally feed this ix86 program to our program logic POG to obtain a verified px86 program, ix86 program. That's all I have to say. Thank you very much for listening.